Hey guys, it's Doc from the Gold Hog, and today this video really is sort of a science breakdown for our new gold Cyclone hyper concentrator, but at the same time I really think if you're a prospector, if you're a miner, if you want to gain any kind of knowledge into the gold recovery field, I think this video is going to be really important for you to watch. I'm going to touch on some of the research we've done. I'm going to blend research that's been out there and been done by major universities and different organizations. I'm going to sort of combine this all, and I'm going to do it in a very simple way. I'm going to keep it in very plain English, and I'm not going to go into different things like Reynolds numbers and laws of physics. I'm not going to get real complicated. And I'm going to try and show it in a way that sort of makes sense, goes pretty quickly, and so you can understand it. Now, the other thing is we're going to go into a lot about vortex capture systems, and I'm going to cover a little bit about the efficiencies and inefficiencies of vortex capture systems, because essentially that's what the gold Cyclone is. It's a water-based vortex, and so I'm going to show you different kind of rules and laws of physics that apply to that and how you can use those to your benefit. But the first thing I'm going to do to you is I'm going to lie to you. One thing that I'm going to show you first is the first thing I did is I took this big heavy, I molded out a lead ball. Okay, so I molded this lead ball out real heavy. I actually polished it down a little bit. It's a sphere and it's made out of lead and it's very heavy. And I'm going to show you something that'll sort of do just a little mind exercise. The next thing I'm going to show you is I'm going to show you a piece of aluminum foil. So you can see that this aluminum foil is very light. So what I really want to show with this example is I want to talk a little about or relate to terminal velocity, settling velocity, specific density. It all ties into this. So here's the pretty simple test that I'm going to show you, and you can do this at home. If you take a big heavy lead ball or rock or even a big piece of gold. So let's say I'm going through fluid, which is air. Air is essentially fluid. So if I hold the piece of foil up here, and if I hold this heavy lead ball, which one's going to hit the ground first? If I let them both go at the same time. Let's try it and let's see. That's a pretty easy test. Let's do it one more time, just to make sure I wasn't wrong. So, light piece of foil, low specific density. Big heavy lead ball, high specific density. Big heavy mass, light mass. Let's go ahead and let's drop them. Ready? Here we go. So we can see that. It almost takes 2 full seconds for that foil to hit the ground. When the ball hits the ground, that heavy lead ball hits the ground in, a 1/10 of a second. So what's the lie that I'm telling you? Well, the lie that I'm telling you is that this isn't a lead ball. That actually this is the exact same thing as this piece of foil. And what I did is I took the exact same size, 4.01 grams of aluminum foil, and I crunched it down and I hammered it and rolled it to give it the appearance of a lead ball. So these two things are identical. The specific density of these two items are identical. The mass is identical. So let's think about that for a minute. Wow, they're identical items. There's nothing different about them. So what's making this do this? Obviously, you can see it very visually in this example that it comes down to the shape of the particle or the shape of the object. So if this was a piece of gold, and if I were to flatten this and flatten this and flatten this out into this shape, guess what would happen? It would have a lower settling velocity. It would have a lower terminal velocity. Everything would change based on the shape of this. And I usually do this. I like to do this. I like to go to the extremes when I do something like this to prove a theory or to get it across to you. This is a really good example of two identical items that are going to have different settling velocities through air and through water. And everything is going to change, the aerodynamic shape. But it's also called hydraulic. So the hydraulic effect on this is that if you were to take, let's say you go to a river. If I was to drop these two, let's say this was a lead ball, or let's just say this is what it is. If I were to go to a river that was running along, and it was, let's say, 24 inches deep, and I were to drop this in the river, it would go into the river, and the ball would fall something like this. A little bit of that force would catch this sphere, a little bit, and then it would fall down the bottom. maybe it would move along the bottom, but it's going to go through that water at sort of an arc shape. And if you ever look at settling velocity charts, that's what you're going to see. You're going to see sort of this arc shape where it goes down and it's going to fall down through. This piece, however, if I were to drop it in a river or a creek that was flowing, it would just keep going. It would settle very, very, very lightly. It barely would settle. And it might go a quarter of a mile down the stream if it didn't hit anything until it found maybe a little corner that it could actually hide behind, a little quiet corner. And if I guarantee you where you'd find this is if you found a big silt bar somewhere, you'd probably find that where it pulled in behind an inside bend or an outside corner or something like that. So that sort of gives you the good proportion that two objects that are exactly the same specific density, the same mass, everything, the shape of those has a tremendous effect on the settling velocity, terminal velocity, everything. Got it? So why is that important? Because today I'm going to really talk about, one of the main things I'm going to talk about hydraulic equivalence. And the one thing I'm going to do is I'm going to hurt your brain a little bit. Now, we're not making this up. This has all been over the years and forever and ever. There's been lots of researchers that have studied this. And there's lots of laws of physics that regard this. But I'm going to hurt your head a little bit. I'm going to read you three little long sentences from different studies. And each one of these studies is about 30 pages long. And there are probably 100 of these. A lot of it has to do with sedimentation, deposits, all kinds of stuff. But just listen to this, and this will help you understand of how I'm trying to make this very simple. First line, hydraulic equivalence. This is the definition. Size-density relationship that governs the depositation of mineral particles from flowing water. Two particles of different sizes and densities are said to be hydraulically equivalent if they are deposited at the same time under a given set of conditions. The smaller particle will have a higher density. Thus, it is not uncommon to find sedimentary deposits containing coarse quartz particles together with fine particles of heavy minerals. Got that? Next one. Fall velocity and drag coefficient expressed respectively are functions of nominal diameter and Reynolds number showing strong correlation over a wide range of shape factors. Analysis of the data by flow regime shows that particle shapes are stronger, that particle shape has strong influence on the settling characteristics when wakes develop behind the grains. That was actually on an ocean study. Settling experiments performed on silt-to-fine silt-sized mica flakes with holographic velocimeter revealed that mica is hydraulically equivalent to quartz spheres having diameter factors 4 to 12 times smaller. Mica, very fine to sand, blah, 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 and it goes on and on and on. So anyways, so what I'm trying to say in this is that we're not out there proving something new. We're just taking all this science and the laws of physics, and I just want to use this to sort of explain it to you. So let's go back to, here's what I want to talk about. When we're running the gold cyclone, vortexes, here's the positive side about a vortex or a cylinder like this. It's extremely efficient on separation, but it uses, some of that separation is based on specific density, some of its mass, but a lot of it has to do as well with the shape of the particles. In other words, there's more hydraulic drag on a flat piece of something than there is on a sphere. So even though this flat piece of something, let's say this is a piece of gold and this is a piece of hematite, even though this piece is going to maybe be heavier specific density wise, the fluid or the force is going to make this travel farther, lower settling velocity. Whereas this one, if it's perfectly round or semi-round sphere, is not going to be affected by that force so much. So these two, even though they're kind of close in size, this one and this one are going to hang together within that flow. And they're going to deposit because they're hydraulically equivalent. Hope you understand that. So I've got a heavy piece of gold, high specific density. Then I take a piece of hematite or a gem that's round. This thing is actually heavier than this thing, but because of the hydraulic equivalence factor, these two will actually travel and deposit together. Make sense? I hope it does. So let me relate all this hydraulic equivalence to you pretty simply. So if I have a piece of gold, let's say I have a piece of gold here, and my piece of gold is about this big and it's flat. Okay, so I have a flat piece of gold here. The next thing I have is I have a piece of hematite, and the hematite is round. Then I have a little small round gold nugget over here. So I have a small gold nugget over here. I have a big flat piece of gold, totally flat. And then I have a round piece of hematite over here. Well, guess what? All three of these things are hydraulically equivalent. So as they're inside of a vortex, they're going to be down at the bottom. They're going to be equal. They're going to equal themselves on their hydraulic equivalence, those three things. So as I put material into a vortex like our cyclone and I set it to a certain range, everything else is going to exit out of there except everything that's hydraulically equivalent. Now that's a positive and a negative. When you go to something like our cyclone, which is a very short cycled 5-10 minute process where you put it in, you run it through, you understand this, and what you understand is that you know that. And you know that what you're going to find is you're going to find small spherical gold, you're going to find small to medium to big size flat gold, and you're also going to have pieces of spheres, heavier gemstones, things that are round. You're also going to have it in there. But what's going to exit out? So if these things are hydraulically equivalent, and these are all inside of my vortex, if these things are hydraulically equivalent, what's exiting out of that? Well, what's exiting out of that? As more and more of these start to build up, there's less room inside that vortex. So what's going to exit out as new water and new material come in? What's going to exit out of here? Well, most people think, and this is an important point, most people think it's just the heaviest stuff based on specific density, and it's not. And that's the important point of this. It's actually hydraulic equivalence. So this piece of hematite, H for hematite, this piece of hematite is hydraulically equivalent to this large piece of gold, as it is to a very small rounder or more round piece of gold. So those three things are going to stay in here. What's going to exit out of here? Well, you're going to have lots of small quartz, silt, mica that's flat. You're going to have flat gold, small flat gold, or very fine gold is going to exit out of here. Irregularly shaped hematites, all kinds of material is going to exit out of here. So their hydraulic equivalence point is beyond the scope of retention here. So when you run this, you understand that. Technically speaking, you could eternally run this thing forever, and what you'd end up with is a batch of specifically together hydraulically equivalent materials sitting right down here. But everything else would be going. So if you continually run this and ran it through tons and tons and tons of material for hours and hours and hours, all of the fine gold would go out of this thing. But everything that was hydraulically equivalent, because you're setting it, and you're controlling it, so I'm controlling it for a certain amount of gold. Understood? So that's where a closed or even a semi-closed vortex within gold capture process really is fairly inefficient on long-term, very high runs. They're great for a cleanup system, for a short run. They're actually very good, but when it comes to long-term, because of hydraulic equivalence, those vortexes become more of a hydraulic equivalence chamber rather than a specific density chamber. Make sense? Now here's another point that you'll want to understand. Man, my board's getting dirty. I want to talk about the ratio of hydraulically equivalent particles. Say that 100 times, it's hard. If I want to go, when I run, especially on my gold cyclone, this is something we noticed, and it just makes common sense. If I have a piece of, let's say, I'm going to talk not about gold, but I'm going to talk about the non-gold material. Well, I'm going to talk about gold too. But let's say I have a piece of gold that big and I have a piece of gold that big. The hydraulically equivalent materials, and I'm blowing this up for you. Let's say that this is a very, very small piece of gold and this is about 1/4 inch piece of gold. So if I cycle down a cycle, I'm going to have, for every one piece of large gold, I may have let's say for every one piece I may have, let's say, 2 pieces of hydraulically equivalent non-gold, so hematite, gems, or whatever, spheres that are round. So for every one piece of this, I'm going to have 2 pieces of hydraulically equivalent non-gold material. It's just what you see. It's just like when you have a bucket. If you fill a bucket full of dirt, if you look at that, you'll see 3 or 4 big rocks. Smaller rocks, you'll see a bunch more, and then as you go smaller and smaller, the piece count explodes. So how many pieces of 1/32 sand do you have inside that bucket of dirt? Thousands and thousands. The same thing happens in this process. So now if I have this, what we find is that we have 1, 2, 3, we have this number starts to get greater. So the smaller gold that we go after, we actually have more material just because of the volume. We have more material for one piece of gold. We may have, let's say, 20 to 30 pieces of hydraulically equivalent material. Make sense? So when I work down a 1/4 inch material, my 1/4 inch materials, I'll have one piece of gold and maybe 2 or 3 hydraulically equivalent rocks that are not gold in there. When I go to fine gold, for every piece of gold I may have 4 to 15 pieces of hydraulically equivalent, just because it's a numbers game. So that there's a lot more of this material, there's a lot more of these little particles to battle than there is at this size. Now I'm going to go off track of this for 1 second and show you how this relates to general mining. I want you to think about different materials and how some of the harder materials to work are in gold prospecting and mining. One of the really difficult ones to do is black beach sands. Why are black beach sands so hard to work? You should already be able to say it right now. Because black beach sands are all fine. You're basically running all fine material. So you have a ton of stuff. For every one piece of gold, you may have 100 hydraulically equivalent pieces in there. So you're dealing with extreme levels of hydraulic equivalence, where you have all these particles that are similar in hydraulic equivalence fighting for the same capture space. If you try and move all these out by speeding up something, well, this one's pretty much hydraulically equivalent too, so it's going to want to move out too. But that's just a good example of how you can apply this kind of knowledge to different types of prospecting. But I want to go over real quick about how this affects closed vortexes and semi-closed vortexes. After a while, if you're running a vortex, let's say I'm using a vortex capture system and I'm going to use that for large-scale mining. So if I'm going to go out there and I'm going to move a lot of material, what's going to end up happening to this vortex? Like I said before, I've got the vortex sitting here, and I'm going to have a whole bunch of larger hydraulically equivalent materials start to build up time after time after time. And to keep this fluid, and to keep it, because it is a vortex in there, and there's water going in, there's water going out, there's incoming force, outcoming force, what's going to go out of here? Well, as this starts to build up, as these hydraulically equivalent particles start to build up in here, there's no more room for fine gold. So eventually, at first it works really well, but eventually as you start to run this, there's no more room at the end for the fine gold. It's taken up by the heavier stuff, and it may not just be gold. It actually may be garnets, it may be hematite, it may be that are round, and they're going to plug up this system in here. So how does this apply to the gold cyclone? This applies to the gold cyclone because the wonderful thing about the cyclone is that it's all based on physics. We don't care about our losses. We know that we're going to have gold depending on the amount of cons we run and depending on how we run the unit. We know we're going to have gold exit the system. That's what it's supposed to do. So I have my cyclone. All right, so I have my cyclone running, and I'm putting material in here. And from what we just learned, I have a vortex or a cyclone operating inside here. So as this material comes down, terminal velocity allows gold to fall farther than it does. Remember the 2 drops I did? terminal velocity. But terminal velocity allows specific density and mass particles to immediately go down. Lighter, like clays and silts, once you get this thing running, they're going to immediately exit out. They're not even going to really fall much into here. They'll fall right about to here, and then they'll eventually work back out. But your heavier materials are all going to fall down here at the bottom. That's why I like to run it two different ways. I run it two different ways because if I have a small amount of cons, let's say 2 or 3 cups, I'll barely have this in a fluid state, bring everything down, and then start the unit to cyclone. If I have a lot of cons, what I'm going to do is I'm going to start this unit spinning and keep it spinning, because a problem that a lot of people have is they think, oh, I'm going to lose some gold. Knock, knock, knock. You're supposed to lose gold. That's the whole point. Your point is hyperconcentration. And what you want to do is get it down to about a tablespoon or maybe 2 tablespoons. You want to take a gallon or half gallon of a quart of these nasty concentrates, and you want to reduce it down to about a tablespoon or 2 tablespoons, whatever it might be. So stuff has got to come out. And part of that's going to be gold that's not what? Hydraulically equivalent. So as you add material in here and you keep it going, you run it and run it, run it. Now if you could run, technically speaking, you could run 50 gallons of concentrates through this. If you kept that energized, and what would you have? If you're running 1/4 inch screen size material, you would have pretty much all 1/4 inch gold and hematite sitting down here. And we have done that. We have put extreme amounts of hematite and gold in here, kept it up real high, and this thing just sits there, and this whole bottom tube basically turns yellow. But anything that's lighter on the hydraulic scale is going to, on the hydraulic or hydrodynamic drag scale, anything that's lighter is going to be going out. But that's the way it's supposed to do. So what do I do next? So the next thing I do is I have a screen. So I have a bucket down here. And now within my bucket, I know for a fact what's going to be in here. What's going to be in here is the next size gold. And I can tell that by just taking this little I call it a screen indicator tube. Sometimes I call it a tailings tube, but tailings indicates losses, unintentional losses, but they're intentional losses. So the tailings tube here will tell me what the next screen size is. So when I shut down my unit, I take this, I put that into a pan, and I pan that out. And if I started with 1/4 inch, if I only see 50 mesh and below gold, guess what? I'm not going to go and screen 1/8 of an inch again and run it, because this thing will tell me what got out of here. That's the beauty about it. You'll typically have about a teaspoon, maybe a tablespoon of material inside this tube that you just got to pan out real quick. But that'll tell you, it's an indicator check. And that's what I really like about this Cyclone is I don't have to go every single solitary screen. In most cases, I don't have to go at every single screen. I can run my material, check it and go, check it and go. And I may only do 2 or 3 screen sizes. So, but the same process applies as you go finer with this. If you screen down to 50 mesh, the same thing is going to happen. You're going to have 50 mesh gold down here. You're going to have 50 mesh material that's spheres that are non-gold, such as hematite and gems, and maybe some pyrite if you find some pyrite spheres. Those things are going to be down here. But the rest of the material is going to go out. So we know it's just based on using physics and hydraulic equivalence that I'm going to go ahead and do this real quickly. I can bring it right out, and I can have everything sitting in a pan. It's about a tablespoon. But one of the questions, the guy that actually invented this system, his initial thought was that it could be used in a commercial type operation or for running raw material. And I pretty much quickly proved that you can't do that because of the hydraulic equivalence. And the one thing you'd have to do is you could run these in sequence, technically speaking, if you had 1/4 of an inch, and if you had 1/8 of an inch, and then 1/16 of an inch. But the problem with that is the screening system. If you're not effectively screening all of your gold out of that material, if you're not screening it constantly and having each screen size go into an individual tube, then it doesn't work. The other problem is what happens, because I told you, what do we learn about time and vortexes? Time and vortexes. Time has a major impact on vortexes. The more material that goes into a vortex, the more what? Hydraulically equivalent material builds up, which means you have to do what? I have to increase my speed. So I'd have to be sitting there constantly increasing my speed with these tubes as they went along. Or I'd have to have a flushing system, a dumping system. So I'd have to actually dump out all those vortexes and restart them again. The problem is it takes forever. I mean, if you're sitting there, you may run, if you run a ton of material, those vortexes by the end of 1 ton are just going to be full. So it just doesn't make sense. Really applying vortex concentration to larger processing, even if you're a prospector with 3 or 4 guys out there, it really needs to be cleaned so often because of hydraulic equivalence. Oh, my board's dirty. So real quickly, after you set up, now one thing I am going to do is I've got some more concentrates raw from the field, and I'm going to run those. I don't know if I'm going to do it on this video or if I'm going to do it on the next video. I'll probably do another video, but I'm going to just go out to the driveway. I'm going to set up my Cyclone, and I'm going to show you how long it takes, because it really is simple. But let me just diagram real quickly how we run this thing based on this science that we have. So all I'm going to do is I'm going to take a bucket of concentrates. I'm going to screen to 1/4 of an inch. So I've got 1/4 of an inch. I'm going to run this through. I run that through my Cyclone. And what's going to come out of there? What's going to come out of there depending on how much material I have. If I only have a few cups of material, I'm probably going to catch a large portion of my gold down to 50 mesh. However, if I constantly have to turn it up and increase the spinning volume to run more and more, I'm going to have more gold go out. So the next step is going to be I may go down to 1/8. So I'm going to classify that. I'm going to run it through the Cyclone, and then what's going to come out? The next thing that's going to come out is going to be, let's say, 30 mesh or 20 mesh, whatever it might be. So I'm just going to constantly just step it down. The beautiful part about this, though, and this is why I really like the Cyclone and why I decided to take this product on, is because of the efficiency of time. All I have to do is I have a small catch can. I take that catch can, I run the material. It takes 3-4 minutes just to run it. Just bring it, dump it in, run it up. Take it. I take that one can out, I screen it out in another bucket, different bucket, and I run it through it again. Start the machine up, boom, run it through it again. Clean in between each cycle. So I will have, the one thing I like to have is I like to have a couple different pans, separate gold pans out, and I dump each one of those runs into each pan. Now, the beautiful part of this, which hydraulic equivalence factors a lot of people think is that is negative, but when you get to the end result of this, it's actually positive. Because let's say I'm on 1/8 of an inch. If I have a piece of gold, and gold very seldom really is round, it's more so either flat or oblong or nuggets or something like that. So I might have a flat piece in my pan, I might have a nugget in my pan, I might have all kinds of weird shapes. But what hydraulically equivalent is going to be in with this material that's not gold? What do we learn? Spheres. So this is a specific density, let's say of 18. Even though my spheres may be a specific density of say 4 to 5, the reason why they're still grouping with this is because they're round. So I'm going to have typically more rounded shapes. I'm going to have rounded shapes, gems, hematites, and so forth. So when I put it into a gold pan, I can put it all in a corner, and all I can do is just sort of let the water just sort of roll. And what you'll see is those rocks roll off. These will roll because they're a little bit lighter and they're round, and the gold will want to stay more so in it. It's amazing. It's a wonderful, that's the thing I like about it the best. Now, as you get smaller, because of the ratio numbers, so if I have, remember I said for larger gold, I might be on a ratio of 2 to 1. So for every big piece of gold, I might have 1 or 2 of these round balls. Well, as I go smaller, I may have a ratio of 4, 5, 6, 7, 8. So it gets a little bit harder. It's a little bit harder to round, but still, you're taking that super fine black sand, and what you're doing is you're concentrating it. So let's see, if you got 2 or 3 cups of that super fine black sand, let's say all 50 mesh, when you run it through the system, you may end up with 2 tablespoons of that stuff, but it's just easier to work. Now if you want to take that and maybe put it to a miller table or put it to something else, it just reduces it down. It's a lot easier. The other thing you'll want to do is when you're running this in your cycles, you'll start to learn pretty quickly. After you do a couple rounds of this, you'll understand where do I want to take my levels. So there are inertia rings, and on those inertia rings, you're going to want to bring it up based on the size. You're going to want to do certain amounts of clearing. And you'll start to see for your type of gold and your type of material, and it's going to vary everywhere, you're going to see what happens on it. Now, real quickly, I'm going to talk about viscosity. And the only reason I'm going to talk about viscosity a little bit is because people want to know if they can run it in a recirculation mode. And viscosity has a really severe impact when you're talking about hydrodynamics. Aerodynamics or hydrodynamics, however you want to call it. But whenever you're talking about the energy of water, I want you to imagine a river that's water that's flowing 20 miles per hour. Well, imagine if the same river was filled with syrup and it was moving 20 miles an hour. It's going to have a lot of energy. It's going to be able to move things. If you were to take, let's say, a piece of metal and drop it into the water, it's going to flow, it's going to settle right down. You drop that piece of metal into that 20 mile an hour moving syrup or motor oil, guess what? It's going to move 4 or 5 times more than the water is before it actually starts to settle. So settling velocity, terminal velocity, everything actually is impacted by the viscosity or thickness of that water. That's why when you're doing this, if you want to rule that out as part of it, plus there's a screening system in the bottom that you don't want to clog up, but you want to have constant viscosity of the water. You will constantly want it to clean. You want things as constant as possible. It's just the laws of physics. You want that viscosity of the water to stay nice and clear and be the same. If you let it get all muddy, guess what? It's going to scrub out. It's going to have more energy. So anyways, I hope this helped, and look for that other, I've got 2 other videos I'll have out on the Cyclone coming up pretty quick.